Hi all. I'm not sure how much I'm going to try to accomplish today. I'm thinking that I'm just going to plow through and give you all the information that you need for the week. And then that way, if you want to break it up, I'll let you know by the time we get to the end of this. But then if you want to break it up and just do some of it today, some of it Thursday, all of the homework will be due on Friday. So just you can kind of plan your week that way, and we will be finished with the chapter on Friday. This is a real quick turnaround for this chapter. It's not a very long one and pretty straightforward, not terribly complicated. We were talking about momentum. Momentum is P is equal to mv, and that means I've got just one object and it's traveling at one speed. But we can change momentum, and if I am talking about the change in momentum, it's going to be one object whose velocity has changed, and change in anything is final minus initial. So change in momentum would be P minus P naught, or mv minus mv naught. All of them say the same thing. The next thing we talked about was the fact that in order for that to happen, there has to be a force, and that force is being applied to the object over a given amount of time. And when that happens, that's impulse. When that happens, you're going to get a change in momentum, cause and effect we talked about. And now I want to just go over a couple of examples of the Ft is equal to mv minus mv naught, and kind of talk through how you would set those up. So we'll start with, I'm going to change my color here. We'll start with 5.2. A golf club strikes a 45-gram golf ball for 6 milliseconds. The club leaves the ball. How about that? The ball leaves the club with a speed of 70 meters per second. Calculate the average force of the club on the ball. And it actually should be 0.6 milliseconds, and so that's what we'll use when we write it down. We're going to do the same thing we did in Chapter 3, where we write down our knowns and our unknowns, and especially we want to pay attention to, are we liking the unit that is involved with that? And so we're going to start right away with, we're told 45 grams, so I know that that's mass. But I also know that grams is not a standard unit in physics, so we're not going to go with that. So we're going to convert that to kilograms, and you do that by moving it 3 places to the left. Another way you could do that is just tack on 10 to the negative 3 like we learned in that first chapter. So I'm going to go with 0.045 kilograms. Absolutely have to have it in kilograms. And its time, the time for that is going to be 0.6. Again, sorry about that. The time is 0.6 milliseconds. And again, millisecond is not a standard unit of time. Milli is 10 to the negative 5, or I'm sorry, 10 to the negative 3. I don't know where 5 came from. Times 10 to the negative 3 seconds. And sorry, I'm a little bit distracted here. I'm at school and there's a lot going on this evening with school board meetings and whatever. So sorry that I'm distracted. I'll try to focus on this. It leaves the club with the speed of 70 meters per second. Now it leaves the club. So the club has been acting on the ball for 0.6 milliseconds. And as it's acting on the ball, that force is applied. That is the impulse, the total force over the total, with the total time that it's being applied. At the very beginning, V naught is equal to 0 because it was just sitting on the T. But my V final then is the 70 meters per second. And the question is calculate the average force of the club on the ball. That would be the sigma F. So I'm looking for sigma F is equal to, I don't know. So let's work through the equation. I look at all of this and I have one equation that accommodates all of that. Sigma Ft, that's my impulse momentum equation, is equal to mv minus mv naught. And I already know that v naught is 0, so I'm just going to get rid of that. So I know that my sigma F times 0.6 times 10 to the negative 3 is equal to my mass, which is 0.045, times my velocity, which is 70. and I'll let you do all the, I mean, I'll do the math for you. If you need to work it through yourself, you can. But sigma F is equal to 5,300. And that would be 5,300 newtons. It's actually 5,250. And in fact, since I've been making a big deal about sig figs, and oh my goodness, some of you are being downright reckless with your sig figs, and you only give me one. If you give me an answer of 0.03, when it really was 0.02834, you have given me one sig fig when you should have given me 3. That should have been your answer, not that. Okay, enough of me being grumpy about that. Please pay attention to sig figs. And the answer is going to be in newtons. Okay, so I just write down my knowns and my unknowns in order to identify where I'm going with this. All right, so then 5.3 is the next one. A car and its 60 kilogram driver traveling at a speed of 8 meters per second, about 40 miles per hour, are stopped abruptly by a collision with the rear end of a parked moving van. The car's front end is pushed in by 0.55 meters by the collision. Stopping distance of the car is 0.55 meters. Calculate A, the time required to stop the car, B, the average force acting on the car, and C, the deceleration of the car. So what's going to happen with this one is I know that I'm going to end up needing, because it's asking for the time. So they were very nice in saying you're going to have to use kinematics to find time, and then once you know time, you can use the impulse momentum equation. But you really could have seen that yourself. I hope that with all that kinematic information, you could have found time, and then from time you can find force. So let's go ahead and write down what we know and what we don't know. We know that V naught is equal to 18 meters per second, and I hope you're doing this with me as we go, so that you're actually having the practice with this as well and not just watching me. So think ahead with these things. You know that V is equal to 0. In fact, let me make a recommendation that you stop the video and actually try to find T on your own, and then turn the video on and see if you and I agreed with it. D is equal to 0.55 meters. Time, I don't know. And I also was given the mass of the passenger is 60 kilograms. Okay, I'm going to look at all those units and I'm going to say I like them all. Meters per second, meters, kilograms, they're all good. So in order to use the sigma ft is equal to mv minus mv naught, then I need to find my t. So let's see what kinematics I have here. I'm looking for this, and I have an equation that actually manages all of that. And the equation is D is equal to V plus V naught all over 2 times T over 1. So my 0.55 is equal to V plus V naught is just going to be 18 over 2 times T. So it's 0.55 divided by 9, and the answer ends up being T is equal to 0.0611 seconds. And now I'm going to look for my force. Sigma Ft is equal to mv minus mv naught. So I don't know my force, but I know that my T is 0.0611. I know that that's going to cancel out, is equal to a negative 60. That's a negative, not another equal sign, 60 times 18. So when I do the math on this, and again, if you need to, go ahead and figure out the math on your own to check to make sure you're getting it. But I'm just going to go ahead and do it here. Sigma F is equal to a negative 1.77 times 10 to the 4th newtons. Okay, now the next question is, I'm supposed to find the deceleration of the driver. There's several ways that I can do that. Now that I know just about everything and I'm looking for A, any one of my kinematic equations could get me there. But there's probably a faster, easier way of doing it. I also know that if I know my net force, let's see, how do I write net force? Average force, net force can be used interchangeably. Sigma F, oh wait, I have a sigma F is equal to MA equation. So I know this, and what an easy way to find this. And by the way, if you went back, it's actually really cool. If you went back and then also did a kinematic equation, you're going to find it works out exactly the same, because the same reality exists whichever direction I come at it. So kind of elegant how physics works that way. I love physics. It's so predictable, and it's so it just always works. It just always works. And it's equal to m, which is 60, times a. And now I just do a division with that, and a is equal to, they said deceleration, so I'm predicting it's going to be negative, and when I do the math, I find it's negative 295 meters per second squared. And if you do further math on it, you would find that that's actually a negative 30 G's. That's a lot of G's on the bottom, on the body. That's pretty tough. And you would do that just by dividing by 9.81, if you're curious about that. All right, there's two more that are actually in the problems, the 5.4 and the 5.6. And what I'm going to have you do is check out the 5.4 and 5.6, do them yourself. I'm not going to give the information here because I really want you to try this one on your own. And when you try it on your own, then you can always go back and check what's happening online. You can check my notes that are already printed online. And then that way you'll know if you're actually picking up on this or not. And check my work. If you're not lining up with mine, see where it's different. I will tell you that mine is right. So just check out how it's different if they don't work out the same. All right, so up to this point now we've done just plain momentum, change in momentum, and what causes the change in momentum. Those are the three concepts we've talked so far. The next thing I want to talk about, I'm sorry that you're getting all those messages, please ignore them. The next thing that I want to talk about is conservation of momentum. And we talked about the fact that momentum is a conserved quantity. And a conserved quantity means that it doesn't change. And what we said earlier was it doesn't change throughout a system or throughout a series of interactions. The momentum in and the momentum out are the same thing. And you can think of that with a Newton's cradle, that when I pull back two of the steel balls in a Newton's cradle and let go, then two on the other end come out the other side. Momentum in, momentum out. So there's a conservation of momentum. So scientists believe that the amount never changes. That's what makes it conserved. And you already know two of the three conserved quantities. I think we might have talked about the other one. You know that energy is a conserved quantity. You know that mass is a conserved quantity, and probably the better way of looking at it now is that the total of those two is a conserved quantity, because mass is being turned into energy every time there's a nuclear explosion. That's what's happening on the sun all the time. And so it's this, the total of energy and mass is actually conserved. It's maybe a better way of looking at it. And then the last one is electric charge. Now, not the total positives and the total negatives, but the total positives and negatives all together, because they move in and out of each other all the time. You maybe remember that from AP Chem or Advanced Chem when you were learning about beta particles or alpha particles, or what's the other one I'm thinking of? Positron. Sorry, positron particles. So they change into each other, but the total does not change. And so the last thing I want you to know is, besides those three, momentum is also a conserved quantity, but it's not an absolutely conserved quantity, and I'll talk about that in a minute. It is universally true that the sum total of energy and mass is conserved literally in the universe. Momentum is within a system, so we'll talk about that in a little bit. You'll see in your notes that there's a derivation for the change in momentum equation, and that's one of the things that I'm going to omit this year. We're kind of tightening things up because we're short on time. So I am going to omit that. You don't need to worry about that derivation. If you want to look through it, it's interesting. I love how we can start with a concept that we know is true, play with it mathematically, and in the end come up with a new equation that actually works out nicely. And I'm just going to go ahead and read so that we're not wasting up a lot of time here. I'm just going to go ahead and read the statement of the conservation of momentum. Again, conservation of momentum means that the momentum into a system, all things being equal, the momentum into a system is equal to the momentum out of a system. And I guess before I read the statement, maybe I've been watching football a lot, go Bills, and when you watch football, you see conservation of momentum all the time. If you have two players that run into each other, and especially if the bigger player, if there's a bigger player and a smaller player, when they run into each other, the total momentum of the two of them is conserved in the collision. They're going to behave differently, but it is going to be conserved. The bigger guy is going to run into the smaller guy, and the smaller guy is going to fly backwards. All of the momentum is conserved, but the momentum of the bigger guy has been transferred to the smaller player, and that's why he flies backwards. But the whole system has maintained its momentum. All right, so that's just an illustration. Here's the statement. When the net sum of the external forces acting on a system of particles is zero, and that's the caveat. That's where I was saying it's not universally true. It's true in a system when this is true about the system. I can't have other forces acting, because if that's the case, then that's impulse. And impulse is going to cause a change in momentum. So there can't be any external forces. It's just the actual objects themselves. So when the net sum of the external forces acting on a system of particles, objects, whatever you want to call it, is zero, the vector sum of the momenta is constant, both in magnitude and direction. So you can't have external or you can't have an unbalanced set of external forces. And when that's the case, again, picture the football players, picture Newton's cradle. The momentum in and the momentum out is going to be the same. Momentum is conserved. Now, I'll post a video of a couple of those things just so that you can get a real good visual about what I'm talking about. But I just wanted to do a couple of applications so that you can see what it is that I mean. So let's look at 5.6. A 30-kilogram boy falls from the roof of a house. After falling freely for 2.5 meters, he lands on the branches of a bush and breaks his fall. He is stopped after sinking 0.8 meters into the bush. Estimate the average force of the bush on the boy. I'm sorry, I'm reading the wrong one. Those were the ones I told you to skip. So let's look at 5.6. A 1,000-kilogram car traveling east at a speed of 15 meters per second has a head-on collision with a 4,000-kilogram truck traveling west at 10 meters per second. If the vehicles are locked together after the collision, what is their final velocity, v? Remember that opposite directions require opposite signs. Now, let me give you what the formula is for the conservation of momentum. The formula is M1, it's kind of an important one to keep in front of you, M1 V1 plus M2 V2 is equal to M1 V1 naught plus M2, plus M2 V2 naught. Now those are pretty self-explanatory, and you can see that I must have two masses now. This is different. This is new. Up to this point, we've been dealing with one mass, and at the very most, we've applied a force to it to change its velocity. Now we've got two objects operating in the system. And conservation of momentum means that when those two objects collide, the total momentum in the system doesn't change. The momentum in, that's this side of the equation, is equal to the momentum out. M1 is the first mass, M2 is the second mass. V1 naught is the speed of the first mass. V2 naught is the speed, the initial speed, that's initial for both of them, the initial speed of the second mass. And then, of course, V1 and V2 are the final velocities. So let's write down what we know here. We know that M1 is equal to 1,000 kilograms. I look at that and I say, I like that unit. That'll work for me. And V1 naught, so its initial velocity, is 15 meters per second. and I know that M2 is 4,000 kilograms, and M2 is initially going at 10 meters per second in the opposite direction. Stop and think for a moment, how am I going to indicate the whole idea of opposite direction? Hopefully you're thinking, okay, opposite directions require opposite signs. I kind of gave you that hint right in the problem. So it's going to be a negative 10 meters per second. And what I'm looking for is the final velocity of the two of them together. And it's actually going to be, because they end up joining up, they lock together, then I kind of realize that V1 is equal to V2 is equal to just V final. Because if they're locked, one cannot be moving faster than another one. So I know that the speed of the first one is equal to the speed of the second one, and so why not just call the whole thing V final? So I'm not dealing with two different variables when they're all the same number. And when you see them joining up like that, that's a good approach to have. I'll also give you an equation that will help with that later on. But right now, let's just use the basic equation we have, which is up here. So I have M1 plus M2. Well, I'll do it this way. So I have M1, which is 1,000, and times V final, because remember I said here V final and V sub 1 are going to be the same thing, plus M sub 2, which is 4,000, V final, is equal to 1,000 times 15, plus, or you could make it minus here because I know it's going to be minus, but it's okay. I'm just going to do 4,000 times a negative 10. All right, so I end up with 5,000 V final is equal to 15,000 minus 40,000. By the time I'm all done and I add it all up, notice that it's going to be negative, so it's going to be 5,000 V final is equal to a negative 25,000. So my final answer then is V final is a negative 5 meters per second. Now that negative is really instructive because what it tells is that my final velocity of the whole thing, that the two of them that lock together are now moving at this speed, but they're moving at this direction. So whatever direction the 4,000 kilogram vehicle was moving, that's the same direction they're all moving by the time it's done. The negative is just as important a piece of information as the 5 is, so make sure you don't forget that. And then let's look at 5.7. 5.7 says a 5,000 kilogram final stage of a rocket ejects the 10,000 kilogram second stage. Before ejection, the two stages together travel with a velocity of 200 meters per second. If after ejection the second stage travels at 50 meters per second, opposite the direction of its initial motion, what is the velocity of the final stage? All right, let's figure out what we know here. So they're calling the parts of the rocket the final stage and the second stage. So I'm going to call the final stage M1. So again, I'm just going to write down what I know and what I don't know here. M1 is equal to 5,000 kilograms, and that's my final stage. So anytime I see final stage, I'm going to associate it with the sub 1. And I also know that M2 is twice as big at 10,000 kilograms. Again, I look at the units, I say, kilograms are good. I like kilograms. Now, initially, they are traveling together. Before ejection, the two stages together travel with a velocity of 200 meters per second. So I know that V1 naught is equal to V2 naught, which is equal to just plain old V naught. I can just call it all the same, which is equal to 200, because they are still attached at that point. So whatever the speed of one is, it's the speed of the other. Then they separate, and V2 ends up going, the second stage ends up going in the opposite direction. The sub 2 is the second stage. It's going in the opposite direction, so I know that I'm going to have to put a negative for my velocity. It's a negative 50 meters per second. And V1 is what I don't know. That's what I'm going to be looking for. By the way, if you had just set this up so that you left V1 naught as 200 and V2 naught as 200, it would not have changed anything. I'm just trying to tighten it up a little bit to make it easier to manage. So let's write down the equation, and I'm gonna tighten that up as well. But if you left the equation like I have up here, nothing would change the answer, so it's fine. But I'm just going to show you a shortcut that you can take if you want to. My first two are together, so I'm going to put them together in my equation. And I'm just going to say, you know what, they both are V naught, like I had said right here. They're both traveling at the same speed. So my M1 is 5,000, and I don't know what speed or velocity it's going when it's done, but I do know that my 10,000 kilogram is going at a negative 50. Is equal to, and I'm kind of running out of room here, if I add these two up, I get 15,000, and they're both going at 200. So I'm going to multiply the 15,000 times 200, and I'll let you take care of the math from there. At this point, you're just going to, this is going to end up being a positive. You move it over there, and you move it here. I'm pointing, and you can't see. These two together are going to end up being positive. So you're going to move it over there by subtracting, and then you're going to divide by 5,000, and you end up getting V1 is equal to 700 meters per second. And because it's positive, it's still going in the direction that they were going to start with. The second stage is what goes in the opposite direction. All right, and now seeing what time it is and what we've gotten done, I think I'm actually going to just quit here. I'm just going to quit here. All right, what I do want you to do for homework, these are, they should be not too difficult. They should be pretty straightforward, but if you run into any trouble with these, let me know. The homework is going to be, you've already done 1, 2, 4 through 6, and then I want you to do, if I have not already assigned it, 11 through 19, 21, and 22. And these are going to be the sigma ft is equal to mv minus mv naught. That's going to be those kinds of equations, or I is equal to ft is also a possibility for that. And then I'm also going to add to that, I know it's a lot, I'm going to give you till Friday to get all of this done, but I would not wait until Thursday night, or you're just going to be dying. And then the last set is going to be 25 through 30. And the 25 through 30 is going to be this equation right here. So you've got those three sets. This one should already be done. The next set of homework should be that equation or this equation. And then the final set of homework is the M1V1 plus M2V2 equation. All right, let me know if you run into any trouble with these. Like I said, they're pretty straightforward. And I'm just about done with the chapter. I only have just that little bit more to do with elastic versus inelastic, which basically takes the one equation that we have and it just starts playing with it so that you don't have to have as much information to start with, and it still works okay. All right, I'm going to pause quite a bit after I'm done with the video because for whatever reason this is just cutting off a ton of time after I'm done with the video. So maybe if I just talk for a little bit more, it won't cut off. So let me ask you this: when we Zoom together, I would love to hear what your favorite Christmas traditions are. So be thinking about that. What would you like